Hi, Stu Schwartz from MasterMathMentor.com. This is video AB37A. The topic is volume, and it covers the AB manual pages 213 through 216. In the last video, we concentrated on area between curves. In this video, we're going to move to the third dimension and start talking about volumes of shapes. Let's start with a simple curve, y equals f of x, which is always positive, on the interval a to b. We are going to take this shape and rotate it about the x-axis. What you get is a three-dimensional object that appears like the one on the screen. If you look at a cross-section of it by slicing it perpendicular to the x-axis, you get a circle. We know that the area of a circle is pi r squared. In this case, the r is the distance from the x-axis up to the point y equals f of x. However, the slice is not really a circle because there is a certain amount of depth to it. We call the shape a disk. The disk in reality is a very thin cylinder whose thickness is delta x. So the volume of our disk is pi r squared times delta x. And therefore, if we add up all the volumes of our disks, we get the limit as n approaches infinity of the summation I equals 1 to n of pi r sub I squared times delta x. We know that is a Riemann sum and can be written as a definite integral. So we have our disk formula, which is really two formulas. The volume of our rotated function about the x-axis is pi integral from a to b of r squared dx if the thickness of our disk is along the x-axis. Our volume of our solid will be pi integral from c to d of r squared dy if the thickness of our disk is along the y-axis. We will see numerous examples of this coming up. We now change the situation just a bit. We add a second curve, y equals g of x, from x is equal to a to x is equal to b. We show this in red and notice that f of x is greater than g of x for all values of x between a and b. We will now rotate both curves about the x-axis. We now see the rotated curves, the outside curve f in blue and the inside curve g in red. We again thinly slice our solid, and any one of the slices we call a ring. It is made up of two concentric circles, the outside circle in red and the inside circle in blue. The solid material is in the blue section. The white section is air. Each circle has a radius. The outside radius in blue we will call capital R, and the inside radius we will call small r. The area of our ring is pi capital R squared minus pi little r squared. And we can then rewrite that as pi times the quantity capital R squared minus little r squared. Realize, though, that our ring has some depth to it. It is really two very thin cylinders. So while there is a capital R and there's a little r, there's also a delta x that represents the height or depth of the ring. And we will call this structure a washer. So, similar to our disk formula, the volume of a washer is pi times the quantity capital R squared minus little r squared times delta x. And therefore, the volume of our solid is the limit as n approaches infinity of the summation I equals 1 to n of pi times the quantity capital R squared minus little r squared times delta x. So we have our second important formula, the washer formula, that says that the volume of our solid is pi integral from a to b of capital R squared minus little r squared dx if the thickness of our washer is along the x-axis. Or volume is equal to pi integral from c to d of capital R squared minus little r squared dy if the thickness of our washer is along the y-axis. The disk and washer formulas are easy enough to use. However, there are decisions that have to be made in order to determine the component parts of these formulas. Here is a surefire way to help you make those decisions. First, draw the graphs in colors, a different color for each equation. And then also draw the equation across the given line of rotation in the same color. If there is only one color on each side of the line of rotation, it is a disk problem, and you need capital R. If there are two colors on each side of the line of rotation, then it is a washer problem, and you need capital R and little r. When we say we need capital R or capital R and small r, we need to represent them as formulas. To do so, we use some basic 8th grade graph theory. When we label a point x, y in the plane, remember that the horizontal distance from the y-axis to the point is x, and the vertical distance from the x-axis to the point is y. This simple fact is instrumental in doing these problems. Finally, even though you have represented capital R or capital R and little r in terms of x and y, they may not be the correct variable for the problem. If the region is rotated about the x-axis or any horizontal line, then the problem is a dx problem and all variables must be in terms of x. If the region rotated is about the y-axis or any vertical line, then this is a dy problem and all variables are in terms of y. We are now going to do a number of problems to illustrate all possibilities. As our prime example, we will start with a defined region and then rotate that region about 4 different lines, showing you all the different variations. Our first region is defined by the curves y equals x squared, y is equal to 0, and x is equal to 2. We draw that graph with the function y equals x squared in blue, the line y equals 0, which is the x-axis in black, and the line x is equal to 2 in red. It is clear what the region is. We will first rotate this region about the x-axis. We draw a mirror image of our curves, and our graph now appears like shown on the screen. This is a disk problem, as there is only one color from the black center of rotation to the curve. We draw a representative disk, shown in color, and then draw the radius, capital R, of that disk from the center of rotation out to the color, and we will label that point x, y. So this vertical distance, capital R, is the value of y. But since this is a dx problem, because the rotation is about the x-axis, capital R must be in terms of x. So since capital R is equal to y, and y is equal to x squared, then capital R is equal to x squared. So we're now ready for our disk formula. V is equal to pi integral from 0 to 2 of x squared squared dx, or pi integral from 0 to 2 of x to the 4th dx. In this problem and all subsequent problems, we will use the calculator to calculate the answer. When we do so, we will ask for a fractional answer, and if possible, the calculator will give it to us. We do not put the pi in to the calculator. We will just attach it to our final answer. So this answer will be 32 pi over 5. Part B is a little bit more complicated. We're going to rotate our region about the line y is equal to 4. Our graph is shown. We draw the curve and then a mirror image of the curve across the line y is equal to 4. So we now have a blue on either side of the line of rotation in green, and also black on either side of the line of rotation in green, meaning that this becomes a washer problem. We draw radius lines from the green line of rotation to the original region, green to black, and green to blue. Capital R is always 4, but little r changes. We draw a representative point xy on the blue curve, and the distance from the x-axis to that point is y. So small r equals 4 minus y. Finally, this is also a dx problem, as we're rotating about a horizontal line. So everything must be in terms of x. So r is equal to 4 minus y, which is equal to 4 minus x squared. We have all the pieces of our puzzle. So using our washer formula, v equals pi integral of capital R squared minus small r squared, v will equal pi, the integral from 0 to 2, of 16 minus 4 minus x squared quantity squared dx. And while we could simplify this, there is no need because we are going to use the calculator anyway. Our final answer is 224 pi over 15. Our region hasn't changed. It is still bordered by y equals x squared in blue, y equals 0, the x-axis, in black, and x is equal to 2 in red. In part C, we're now going to rotate the region about the y-axis, and our graph is as appears. We draw a mirror image, and we see that this is a washer problem because there are two colors on each side of the line of revolution, the y-axis. We draw a representative washer, red to red, blue to blue. It is clear that capital R is always 2, but the inside radius, little r, varies. So we label a point on that curve as xy, and we see that little r is equal to x. But this is a dy problem, as washers are stacked vertically because we are rotating this about a vertical line. So variables must be in terms of the variable y. Since y is equal to x squared, x is equal to r, which is equal to the square root of y. We are now ready for our formula. Realize that our integral no longer runs from 0 to 2, but from 0 to 4 as we are integrating along the y-axis. So our area is equal to pi integral from 0 to 4 of 2 squared minus the square root of y squared dy, which is pi integral from 0 to 4 of 4 minus y dy. This tough-looking problem turns out to be a very simple integral, and our answer is 8 pi. In part D, we will rotate our region about the line x is equal to 2. And again, we draw the graph. We draw a mirror image across that line and see that we're back to a disk problem. A representative disk is drawn, blue to blue. We only need a capital R for this problem. Capital R is shown on the graph, the distance from the red to the blue. If we label our point xy, we realize that our distance from the y-axis to the red line is 2. And therefore, the distance from the y-axis to the point is x. So capital R has to be equal to 2 minus x. But again, this is a dy problem, so capital R is equal to 2 minus the square root of y. Once you have all the pieces of the puzzle, the answer is easy. V is equal to pi integral from 0 to 4 of this quantity 2 minus the square root of y, quantity squared, dy, which is 8 pi over 3. When you are doing these problems, remember that you are creating a three-dimensional shape. It is sometimes interesting to imagine what kind of real-life object this shape is creating. In the case of D, the top part of it appears to be very similar to a Hershey kiss, as shown on the screen. In number 2, our region is defined by y equals 2x, y equals 0, and x is equal to 3. We are going to rotate this region around 3 horizontal lines. We first rotate our region about the x-axis, and since there's only one curve, it is a disk situation. The radius is y, which is equal to 2x, as this is a dx problem. So v is equal to pi integral from 0 to 3 of 2x quantity squared, which is 4x squared, dx. And this turns out to be 36 pi. In B, we rotate our region about the line y is equal to 6. So we draw a mirror image of our region across the line y equals 6, and we see that this is a washer situation with the outside radius 6 and the inside radius 6 minus y, which is equal to 6 minus 2x, as again, this is a dx problem. So therefore, v is equal to pi integral from 0 to 3 of capital R squared, which is 36, minus little r squared, 6 minus 2x quantity squared, dx. And our answer is 72 pi. We now rotate our region about the line y is equal to 8. Again, we draw a mirror image of our region across the line y is equal to 8, And we see again that this is a washer situation with the outside radius as r and the inside radius as 8 minus y, which is equal to 8 minus 2x, as this is a dx problem. And therefore v equals pi integral from 0 to 3 of capital R squared, 64, minus little r squared, 8 minus 2x quantity squared dx, and our answer is 108 pi. We now rotate our region around 3 vertical lines, making them dy problems, as our discs or washers will be stacked vertically. In D, we are rotating our region about the y-axis. We draw our region across the y-axis and realize that this is a washer situation, with capital R always being 3, but little r being the x variable. And since this is a dy problem, we have to solve for x, which is y over 2. So v equals pi integral from 0 to 6 of capital R squared 9 minus little r squared y squared over 4 dy. And our answer is 36 pi. This is integrated from 0 to 6 because y starts at 0 and goes all the way up to 6. In E, we are rotating about x equals 3. We draw our mirror image across the line x is equal to 3 and see that this is a disk situation. The radius is 3 minus x, which is 3 minus y over 2. So therefore v equals pi integral from 0 to 6 of capital R squared, which is 3 minus y over 2, quantity squared dy, or 18 pi. In F, we are rotating about the line x is equal to 4. We again draw our mirror image of our region across the line x is equal to 4 and realize that this is a washer situation, with the outside radius being 4 minus x, which is 4 minus y over 2, while the inside radius is always 1. And therefore v equals pi integral from 0 to 6 of quantity 4 minus y over 2 quantity squared minus 1 dy, which is 36 pi. In number 3, our region is defined by y equals 1 plus the square root of x. The horizontal line y is equal to 1, and the vertical line x is equal to 4. It is a clearly defined region, and we are going to rotate it around first 3 horizontal lines. In A, we are rotating about the x-axis. We draw the region across the x-axis, and we see that we have a washer situation. Capital R is equal to y, which is equal to 1 plus the square root of x, while little r is equal to 1. So therefore v is equal to pi integral from 0 to 4 of the quantity 1 plus the square root of x, quantity squared, minus 1 dx. Final answer is 56 pi over 3. In B, we are rotating around the line y is equal to 3. We again draw a mirror image, and we see that again it is a washer problem, with capital R being the distance from 1 to 3, which is 2, while little r is equal to 3 minus y, which is equal to 3 minus quantity 1 plus the square root of x, which is 2 minus the square root of x. So therefore v equals pi integral from 0 to 4 of capital R squared 4 minus little r squared, quantity 2 minus the square root of x, quantity squared, dx. And this turns out to be 40 pi over 3. In C, we are rotating around the line y is equal to 1. So again, we draw a mirror image across that line and we see that it is a disk problem. And therefore, capital R is equal to y minus 1, which is equal to 1 plus the square root of x minus 1 or the square root of x. And therefore, the integral is simple, pi integral from 0 to 4 of x dx, which is 8 pi. In D to F, we are now rotating our region about vertical lines, and these will become dy problems. In D, we are rotating our region about the y-axis, and this becomes a washer situation. Capital R is 4, while little r is the x variable. And we solve for x in terms of y, and we get x is equal to y minus 1 quantity squared. So v now is pi integral from 1 to 3 of capital R squared, which is 16, minus little r squared, which is y minus 1 to the 4th dy, or 25.6 pi. This integral goes from 1 to 3 because our washers are stacked, starting at y is equal to 1 to y equals 3 vertically. E rotates our region about the line x is equal to 4. And when we draw this, we see that this is a disk situation, as there is only one curve to the left and to the right of the line of rotation. Our capital R is 4 minus the x variable, which is 4 minus quantity y minus 1 quantity squared. So v is equal to pi integral from 1 to 3 of 4 minus the quantity y minus 1 quantity squared, the whole thing squared, dy, which is 17.067 pi. Finally, we are rotating around the line x is equal to 6. This is a washer problem, as there are two curves to the left and right of the line of rotation. Capital R is 6 minus the x variable, which is 6 minus quantity y minus 1 quantity squared, while little r is always equal to 2. So v is equal to pi integral from 1 to 3 of the quantity 6 minus quantity y minus 1 quantity squared, the whole thing squared, minus 4 dy, which is 38.4 pi. This problem is a good illustration that there are no generalizations that can be made, like rotating about the x-axis produces disks, while rotating about the y-axis produces washers. Every problem must be decided on a case-by-case basis. It all comes down to whether there is just one radius creating disks or an outside and inside radius creating washers. Number 4 asks to rotate the region between the curves y equals x squared and y is equal to the cube root of x around 3 different lines. We draw the curve and show that they both go through the point 0, 0 and 1, 1, and the area in gray is clearly defined. We first rotate about the x-axis, and we see by the graph that this is a washer situation. The outside radius and the inside radius are both the y variables, with capital R being the cube root of x and small r being x squared. So therefore v equals pi, the integral from 0 to 1, of capital R squared, which is x to the 2/3, minus little r squared, x to the 4th, dx, which is 0.4 pi. We next rotate about the y-axis. And again, when we draw it, we see this is a washer situation with capital R and little r each now equaling the x variable. So we have to solve each of the equations for x, and we get capital R is the square root of y, while little r is y cubed. So therefore v equals pi integral from 0 to 1 of square root of y squared, which is y, minus y cubed squared, which is y to the 6th dy, and our answer is 0.357 pi. We now rotate around the line y equals 1. This again is a washer situation with capital R and little r both equaling 1 minus y. So capital R is equal to 1 minus x squared, and little r is equal to 1 minus x to the 1/3 power. So therefore v equals pi integral from 0 to 1 of 1 minus x squared, quantity squared, minus quantity 1 minus x to the 1/3, quantity squared, dx, and our answer is 0.433 pi. In number 5, our curves are y equals e to the x equals 0, which is the y-axis, y equals 0, which is the x-axis, and the line x is equal to 1. Our region is well defined, and we would like to rotate this region around 3 different lines. We first rotate our region about the x-axis. This is easy. It is clearly a disk problem, and capital R is equal to y, which is equal to e to the x. So v is equal to pi integral from 0 to 1 of e to the x quantity squared, which is e to the 2x dx. And our final answer is 3.195 pi. In B, we are rotating our region about the y-axis. And this is where things get a little bit more complicated. We draw the picture and we realize that there are 2 things going on here. First, we seem to have disks in play from y equals 0 to y equals 1. And then washers take over from y is equal to 1 to y is equal to e. So for the disk part of the problem, capital R is equal to 1. And for the washer problem, capital R is equal to 1, and little r is equal to x, which is equal to the natural log of y. Therefore, v equals pi integral from 0 to 1 of capital R squared, 1 dy, plus pi integral from 1 to e of 1 squared, 1, minus the natural log of y squared dy. And when you calculate each part, you get pi for each. And therefore your answer to this problem, interestingly enough, is exactly 2 pi. In C, we are rotating about the line x is equal to 1. When we draw our region, we realize that we have 2 disks in place. The first disk is in operation when y starts at 0 and goes to 1. And our second disk is in operation from y equals 1 to y is equal to e. So for the lower disk, capital R is equal to 1. In the upper disk, capital R is equal to 1 minus x, which is equal to 1 minus the natural log of y. So our volume is the sum of 2 integrals. The first integral is pi integral from 0 to 1 of 1 dy, and the second integral is pi integral from 1 to e of 1 minus the natural log of y, quantity squared, dy. The first integral is pi, the second integral is 0.437 pi, and our final answer is 1.437 pi. In number 6, we see the curves y is equal to 1 over x plus 1, y equals 0, x is equal to 0, and x is equal to 1. and this gives the region shaded in blue. We will first rotate about the x-axis, showing a mirror image across the x-axis, which is A. Then around across the line, y is equal to 1, and the mirror image is in B. Then the y-axis, which gives the mirror image in C, and then the line x is equal to 1, giving the mirror image in D. And we would like to compare all four volumes from the highest to the lowest. In A, we are rotating about the x-axis. This is a disk situation with capital R equaling y, which is 1 over x plus 1. So V equals pi integral from 0 to 1 of 1 over x plus 1 quantity squared dx, which is 0.5 pi. In B, we are rotating about the line y is equal to 1. This becomes a washer situation with capital R equal to 1 and small r equaling 1 minus y, which is 1 minus 1 over x plus 1. So V equals pi integral from 0 to 1 of the expression 1 minus quantity 1 minus 1 over x plus 1 quantity squared dx, and that is equal to 0.886 pi. Parts C and D rotate about vertical lines, which means that we're going to have to solve for x in terms of y. So if y is equal to 1 over x plus 1, then x is equal to 1 over y minus 1. Part C rotates about the y-axis. This is, similar to the last problem, two disk situations. The lower disk is in place from y equals 0 to y equals 1/2. And then the second washer situation is from y equals 1/2 to y is equal to 1. So for the lower washer, capital R is always equal to 1. But for the upper washer, R is equal to x, which is equal to, as we just saw, 1 over y minus 1. So therefore, V equals pi integral from 0 to 0.5 of 1 dy plus pi integral from 0.5 to 1 of 1 over y minus 1 quantity squared dy. And when we do the math for each, we end up getting 0.614 pi. D rotates about the line x is equal to 1. And again, similar to the previous problem, this is first a disk situation and then a washer situation. For the disks, R is equal to 1. For the washer, R is equal to 1, but little r is equal to 1 minus x, which is 2 minus 1 over y. So V is equal to pi integral from 0 to 0.5 of 1 dy plus pi integral from 0.5 to 1 of 1 squared, which is 1, minus 2 minus 1 over y quantity squared dy. And our answer is 0.773 pi. So the answer, which is largest, is rotating around the line y is equal to 1. The second largest is rotating about the line x is equal to 1. The third largest is rotating around the y-axis, and the smallest is rotating about the x-axis. Note that the mirror images across the respective lines, A, B, C, and D, all have equal areas to the original region in blue. However, when they are rotated around those lines, the volumes are not the same. We have not quite yet completed our study of volume. We have looked at volumes of rotation, but there are other types of volume problems that we can examine, and in video 37b we will do so.